So let's just do this show how to do this in our data set. So I'm interested in, let's say, the agriculture coefficient from this Swiss data, and I want to know what's the variance inflation by including examination and education, and I'm sorry, examination and education together. So I get sort of that 90% increase in variance when I include examination, and then 100% increase in variance when I include examination and education. Now again, this is variance inflation is just part of the picture. I think in this model we would want to include those because we would want to see, is the agriculture effect attributable to some of these other effects. So, and you can get the variance inflation factors, which is you get a variance inflation factor for every coefficient, and it's the comparison of how much variance is increased compared to if all the covariates were orthogonal. And you can see some of them, it's clear things like education and examination are very high, right? Because they're very correlated with each other, right? By the way, I like square rooting the variance inflation factors, the standard deviation inflation factors instead, I guess. But that's so you can use these to see kind of for a given covariate how much variance it appears to be adding relative to a model where had all the covariates been orthogonal. Okay, so what happens to residual variance estimation when we forget or omit or include variables that we should have or shouldn't have? So again, we're going to assume the model is otherwise right. So linear IID errors, finite variance. Then we can describe the mathematical impact of omitting necessary variables or including unnecessary ones. So if we underfit the model, i.e. if we don't include necessary variables, we omit necessary variables, then the variance estimate is biased. If we overfit the model, then including all necessary covariates and unnecessary covariates, then the variance estimate is unbiased. So expected value, so in that case, if we include all the necessary covariates and any unnecessary covariates, then expected value of sigma hat squared is sigma. However, the variance of sigma hat squared, including unnecessary covariates, is going to be greater than the variance of sigma hat squared, including only the correct covariates. So there is no free lunch. You can't just say throw in all the covariates and I'll get an unbiased estimate of sigma squared. There's a consequence. The variability in that estimate of the variance gets worse. Okay. So covariate selection. I'm not going to talk too much about covariate selection because we have an entire class on machine learning, and that's kind of the modern way to think about it. But automated covariate selection is a difficult topic, and and it depends on how rich of a covariate space you want to explore. Even with small numbers of regressors, the space of models explodes quickly as you add interactions and polynomial terms. And so in your prediction class, you'll cover many methods for traversing very large model spaces for the purposes of prediction. If you want to do regression, things like principal components or factor analysis models are often useful for taking complex covariate spaces and reducing the dimensionality. I would say if you're really interested in parsimonious small effects, then consider focusing on design, right? The best example is randomization. But you could also have things like randomization, stratification, and other things that can make your regression model not have to be very complicated because you've put a lot of thought into the design. So if models are interested in, if the models that you're interested in comparing are nested, in other words, one is a special case of the other with coefficients set equal to 0, and there aren't a lot of parameters in differentiating the two models. So if you want to compare a model with two terms in it to the model without those two terms, then you can just use nested likelihood ratio tests, and I'll show you how to do that in R. If you have zillions of variables that you're choosing whether or not to include, then probably you don't want to do this. But if you just have a couple, then this is a reasonable thing to do. My favorite approach is I tend to think in terms of scientific context, and so if I see an effect, a treatment effect or something like that, or an effect due to some important variable, then I like to use my modeling as a way to probe and test the robustness of that effect. Does my treatment effect, does it go away if I include age? Does it go away if I include BMI? And it's an approach of tinkering around with the models and seeing how robust the effect is to other variables included or excluded. And that's kind of a non-systematic process, but I feel like when you do that, you learn a lot about the data, and that's why I like it. And it's completely non-automated, but I do like to think about things that way. It would not work for things like prediction, but it does work extremely well for doing things like trying scientific discovery. So at any rate, if you want to do nested model search, right, if you want to do a nested model search, so take as an example, I'm interested in this agriculture coefficient, but I want to know whether or not I need to include the educational covariates as a group, and then whether I should need to include these other covariates, Catholic and infant mortality, as a group. If you just fit all three models, and the update function just says keep everything the same except in this case, the model, then the ANOVA function will create this series of likelihood ratio tests for you. So here, the output, it gives you the models that you're fitting. It gives you the degrees of freedom, which drop down. So we start out with 45 residual degrees of freedom. That's n minus p, and then we lose 2 more because we've added 2 more coefficients, and then we lose 2 more because we've added 2 more coefficients. So this degrees of freedom is the degrees of freedom for the comparison. So the comparison between these two models, you have 2 parameters difference. For the comparison between these 2 models, you have another 2 parameters difference. So this comparison compares it to the previous one. So it compares 2 to 1 and then 3 to 2, and that's what that p-value in each case is giving you. So in this case, it's saying the p-values are saying yes, that you should include these educational components, and then the p-value is saying yes, if you include the educational components, then you should also include this Catholic and infant mortality variables. So that's how you can do nested model testing in R. The one thing is you had to have this ordering, right? You had to have agriculture, then this block of variables you were going to include in the second model, and this block of variables that you were going to include in the third model. So if your thinking and strategy fits into that framework, then that's a very good thing to do.